Okay, as Pooja said, this is some work that Burgess and Neipel did for the Ohio Department of Transportation. And this originated because ODOT was having some problems with their skewed bridges. And this focuses mainly on steel eye girders because that's where most of the problems were. But although it does focus on steel eye girders, a lot of these principles apply to any type of skewed bridge. The problems ODOT was experiencing was mostly related to deck pours. And what they were finding was that the deflections predicted in the plans were often wrong, and they led to incorrect screed elevations, which in turn led to poor finishes and inconsistent thicknesses in the decks. Another problem that arose was twisting of the girders, and they were experiencing excessive twist, especially in heavily skewed structures. And this in one case led to replacement of structure after only a few years of service. So the questions that they wanted us to address: so why was this happening? What kind of analysis methods can we use to predict this behavior? And how can we prevent this from happening in the future? So the first portion of the presentation will be an overview of how skewed bridges behave. And the first bullet here is a basic statement about skewed bridges, that introducing skew into a structure produces effects that can't be predicted using line girder analysis. And what I mean by line girder analysis is just a single girder, looking at a single girder at a time without considering the effects of the cross frames. So with a straight, non-skewed bridge, you can generally look at a single girder line and get a pretty accurate picture of how the bridge is going to behave. And this is commonly how simple bridges are designed. But in a skewed structure, the girders interact with each other and distort the behavior of the individual girders. And that needs to be taken into account in many cases. And I also refer here to the AASHTO NSVA guidelines for the design for constructability, which is a great source for a discussion of this material on skewed behavior. And it divides the behavior into two separate categories, which is intermediate cross-frame effects and end cross-frame effects. And we'll discuss both those in turn. So starting off with the intermediate cross-frame effects, this is a test case we use to illustrate what those are. This is a simple span structure with a 150-foot span and a 60-degree skew. And there are 5 girder lines spaced at 9'6" on center. And you note that the intermediate cross frames are perpendicular to the girders and the end cross frames are skewed, which is the typical configuration for this kind of bridge. And we'll start off by looking at the structure ignoring the cross-frame effects. So if we look at each girder individually, we're looking at the deflections during the deck pour. If we load it with the deck weight and look how they deflect, what we have is a uniform loading on the interior girders and slightly lower loading on the exteriors due to the overhangs being slightly shorter than the interior bays. And we should note about this, each of the vertical lines represents a cross-frame location. And if you look down each one of these cross-frame locations, you see kind of irregular spacing between the deflections of the girders. And if you look at that in section, what you see is that you get kind of an irregular shape across the width of the structure. The blue numbers on the top are differential deflections between the adjacent girders. The red numbers on the bottom are the girder deflections. And the important point about that irregular shape is that by ignoring the cross frames, we get a deflected shape that can't really happen. The cross frames connecting these girders are very stiff, and they torsionally restrain the girders so that this shape isn't really possible. the conclusion that we can draw from this is that we need to consider those cross frames in the analysis. And here's a simple diagram of how the cross frame functions. So if you have differential deflection between adjacent girders, and you assume the girders don't twist, you have to assume there's axial deformation in the cross frame members. And it takes a lot of force to deform those members axially. So the resistance to this type of movement is really high. However, if the girders twist, the cross frames don't have to deform. They can just go along for the ride with the girders. And torsionally, eye girders are very flexible, so they don't put a lot of resistance up to this type of movement. So this is the common behavior that you see in skewed structures and also in curved structures. So going back to the test structure, you can now look at a grid analysis of that structure, which considers the cross frame effects. And the deflection patterns look significantly different. If you look down the cross frame lines, you get relatively even spacing between the deflection girders, the differential deflections between the cross frames. So if we look at that in section, at the top we have the section with the cross frames effect ignored, the line girder model. And below we have the grid model, which considers the cross frame stiffness. And with the line girder model, you can see the abrupt changes. With the grid model, you get relatively smooth section that makes a lot more sense. So the next several slides are a walkthrough of how a skewed bridge deflects when you consider the effects of the intermediate cross frames. And note, we don't have any in cross frames in this structure yet. We're looking only at the intermediate cross frames. So starting off here with section AA, you can see girder 4 is very close to its bearing point. Girder 5, we're out in the span, so girder 4 is staying up, small deflections. Girder 5 is deflecting, so we get a big differential there. We get similar behavior here. We've got girder 3 at its bearing point, so everything's falling away from 3. Again here, girder 2 and a girder 1. So we're leaning away from that support. As we cross out into the span, the structure starts to flatten out. We get near mid-span, it's relatively flat, starting to reverse itself. And when we get to this section, we've got now girder 5 near our bearing point. The structure's falling away from 5. Again at 4, and at 3, and at 2. So over the length of that structure, you get a total reversal in the shape, so that you have opposing twists at each end of the structure. Now another effect of the intermediate cross frames is a redistribution of loads across the bridge. And the easiest way to see that is to look at the support reactions at each end of the bridge. The reactions for all the bearings are plotted on the chart at the bottom of this slide. The rear bearings on the left, forward bearings on the right. The black line is what was predicted using line girder analysis without considering the cross frames. The pink line considers the effects of the cross frames. So you can see when the cross frame effects are considered, you get a large peak at the obtuse corner of the framing that you miss in a line girder analysis. So it shows that the intermediate cross frames also have a significant effect on moments and shears within those girders as well. Moving on to the effects of the end cross frames. These are entirely independent from the intermediate cross frame effects. And to illustrate how this works, I'm using an example. This is borrowed from a paper by Fred Beckman and Ron Medlock. This is a two-girder bridge with end cross frames only. And this is just a generic single span bridge and the skewed in cross frames. And here's an isometric view of that bridge showing the in-cross frame. For simplicity, you can idealize that in-cross frame as just a pair of rigid links that connect the top flange of one girder to the bottom flange of the other girder. And it's we're talking about in-cross frame effects. It's important to think about the mechanics of how the girders deflect. And this drawing shows the cambered and the deflected position of a single span beam. So the OH variable is the overhang length prior to deflection. And the delta is the initial camber, the deflection of the position of the top flange in the initial cambered position. And here the left bearing is fixed in this example. So when the girder deflects, it decambers. It makes the bottom flange longer and the top flange shorter. And the important point here is that the top flange and the bottom flange move relative to each other when this happens. Here's a plan view showing what happens as the top flange tries to deflect longitudinally relative to the bottom flange. The bottom flange of girder A is restrained at the fixed bearing, so it can't move. And the top flange of B must move longitudinally as the girder decambers. But since this girder is restrained, it can't move straight as shown here. It has to move radially about the bearing point of girder A. So it gets pulled over as it moves forward. So through this kind of action, the in-cross frames cause twist independently of the intermediate cross frames. Here you can see both girders acting simultaneously. And the resultant direction of that movement is approximately perpendicular to the bearing line for those girders. Here's a comparison of the girder twist calculated for the in-cross frames only versus the twist calculated for the intermediate cross frames only. And you can see that the magnitude of the twist is about the same for both, with the in-cross frames are a bit more uniform across the width of the bridge compared to the intermediate. But if you combine those effects, you have in-cross frames, intermediate cross frames in together. The top shows the two effects independently. The blue numbers are the intermediate effects. The red numbers are the end effects. The bottom diagram is the combined effects. They're approximately equal. So both the intermediate and the in-cross frames produce this twist independent of each other, but they're not additive effects. They both acting together produce about the same amount of twist. So moving on now to the parametric study we did. Many of ODOT's problems originated from the analysis methods being used by designers. Prior to the change in policy, it was common practice to use line girder analysis for almost all skewed bridge designs. But based on recent experience and based on our study of skewed bridge behavior, it was clear that that was not appropriate, at least not for all structures. So the question we were trying to answer is what level of analysis could be used for which structures. And obviously we could use a detailed finite element analysis for every bridge, but that raises the design costs and limits the number of consultants that are able to do these designs. So ODOT wanted us to do a study of various different types of structures, determine where the line is where you need to start using advanced analysis methods. So for we did different combinations of line girder only, 2D grid, which is basically all beam elements, which is what MDX and Deskus software, which are the common prepackaged softwares to do grid analysis used by most of the consultants in Ohio, what are used, and then also a couple different levels of higher level analysis, a 2D grid using cross frames, so modeling the depth of the cross frames and all the members, and then a full 3D finite element with plate elements. And we initially did these models, it's done a few years ago in STAD. We've since upgraded those to Midas. Midas provides a lot more powerful tools for us to use as far as staging and processing the results. It's been very helpful. This is a basic explanation of the model types we used. A line girder, as I stated before, is just a simple single girder beam element model. And then the 2D grid, this is as modeled using MDX or Deskus, uses beam elements to model the cross frames. And it should be noted that this model is approximate because you can't fully model the cross frame behavior with a single beam element. And both of those two programs, you do it slightly differently. For the advanced models, we used an advanced grid analysis with individual cross frame elements modeled for the truss elements, modeled with truss elements, and a 3D finite element model. We used shell elements for the webs and the flanges, and truss elements for the cross frames. And obviously, as the precision of these models improves, as they become more complex, but data processing for design also becomes a lot more time intensive as the model gets more complex. So we made some pretty straightforward conclusions from this study, and I'll walk through the important ones here briefly. As expected, there's a significant difference between the results obtained between the line girder model and any model including cross-frame effects. But in general, line girder analysis was conservative for the calculation of moments and shears because of the distributing effects of the cross frames generally lowered the moments and shears on the individual girders. And only with the structures with a 60-degree skew did we have moments and shears exceeding those predicted by the line girder models. Here we're comparing the results of the basic 2D grid using MDX or Deskus with a higher level model in STAD or Midas where truss element cross frames were used. For the structures examined, these two methods produced very similar results in terms of moments and shears. So the conclusion here is for a simple skewed structure, and these are all very simple structures, just single span, constant skew, a basic grid analysis is accurate enough to predict the moments and shears. But I want to make clear that the intent here is not to dissuade designers from using higher levels of analysis. It's just and it's recommended that you use those levels for more complex structures with variable skews or partial length girders. But ODOT's goal here was to set a minimum required analysis level, and for a basic structure, a grid showed itself to be sufficient. And the final comparison here was between a 2D and a 3D model. And again here, for simple structures, there's little difference between the calculated moments and shears. But 3D has a number of advantages in that it's required to accurately calculate the lateral bending or the warping stresses in the girder flanges, which can be significant when you have a heavily skewed structure. And there are more factors than skews that should be considered when you're selecting an analysis method for a structure. So a little discussion of detailing methods here. And in a skewed structure, the girder can be plumb only under a single loading conditions. Which loading condition this is depends on the detailing of the cross frames. The method that had been commonly used in Ohio was steel dead load fit, meaning that the girders are erected under steel weight only in a plumb position. So when the girders are erected, the cross frames are installed prior to the deck pour, everything is plumb. And then when the deck pour happens, the girders are loaded, the girders go out of plumb. And the outstanding question is, in ODOT's mind anyway, was how much twist is acceptable in that method? When does it become a problem? An alternative method is to use full dead load fit. Here the girders are out of plumb when they are erected, meaning that the cross frames are sized to fit in the finished condition rather than in the erected position. So the girders have to be forced into position when the cross frames are installed. They're forced into a twisted orientation. Then, if everything deflects as predicted, when the load is added, the girders will then rotate to plumb in the finished structure. And this is the method that's generally recommended by industry experts for detailing a skewed structure. But ODOT has made the decision that they're not comfortable with this method of erecting the beams. They feel that this contradicts too much of their past practice, which is they prefer to erect the girders plumb, and then they're going to limit the twist in the design stage. Third method that we looked into in this study, which is lean-on bracing. And in extreme cases where twist can't be controlled otherwise, you can use an alternative lateral bracing system to control the twist. Since cross frames are the source of the twist, eliminating some of the cross frames can reduce the twist. So in this configuration, some of the cross frames are replaced with top and bottom struts only, so that they'll restrain the girders laterally but not torsionally. And these braces allow differential deflection to occur without inducing twist in the girders. So there are a couple different ways you can use lean-on bracing. We termed them internal and external. An internal system, you have cross frames within the loaded portion of the bridge. So here we have deck being applied to this system of girders. We have a cross frame, and then we have a series of lean-on braces. When the system deflects, you will get some twist in this section, in this system. But you can limit it by carefully placing the cross frames in places where there is not a lot of differential deflection. And it does require a refined analysis to predict forces and deflections of this system. Here's an example of a framing plan for an internal lean-on system. There has to be at least one cross frame in each line of braces to ensure that it's stable. And the designer does need to do calculations to ensure that you've got enough strength and enough stiffness to adequately brace all those girders. Second form of the lean-on system is to use an external lean-on system. And in this case, you do not have any cross frames within the loaded portion of the bridge. You're braced to an external point. The way this has been used previously is with stage construction. You brace to another portion of the bridge that's not going to have the deck loaded on it, so that when this portion deflects, there's no cross frames to torsionally restrain the girders. They can go straight down, and they all stay plumb, ideally. Moving on, the final question that ODOT wanted answered as part of this study is, can we predict twist without going to a grid analysis? Can we do it from line girder results only? And we devised a method to do this just based on measuring the differential deflections between adjacent girders using a line girder analysis. And came up with a rule of thumb that we found to be conservative up to a 45-degree skew. If you measure the differential deflections, this is based on a 1/8 inch per foot of web depth as an allowable tolerance for rotation. That comes from the erection tolerance from the AASHTO NSBA erection guide specification. So if we go from that tolerance and assume that the two girders rotate as a unit, you can derive a relationship of a deflection equal to the girder spacing divided by 100 approximately corresponds to that 1/8 inch per foot. So the rule of thumb established was if your differential deflections are less than girder spacing divided by 100, then twist will be within tolerance. So moving on to the policy itself, it's laid out here in flowchart form. And I'll start with an explanation. ODOT's philosophy on skew is that for a long time they designed skewed bridges using line girder analysis and had no problems. But as codes changed, higher strength steel came into being, and structures got more flexible, they started to have problems. So their general preference is stick to line girder analysis wherever possible, keep it simple, and try to solve the problems by stiffening the girders first. And that creates, in their opinion, creates a more durable structure over the long term. So in general, they prefer to spend their money on more steel rather than more analysis. And then as people who analyze bridges for a living, we may not necessarily agree with that decision, but it does have merits in their opinion. So that said, this is the policy. For skews less than 30 degrees, you're exempt from the policy, and line girder analysis is acceptable. For skews from 30 to 45 degrees, you start the process on the left side of this flow chart, which will, and for skews greater than 45, you start on the right side, and then we'll walk through each of those in turn here. So for skews from 30 to 45, the first step is to perform line girder analysis and use the S/100 rule of thumb. If you meet that requirement, you're okay, and you can proceed designing the bridge using line girder analysis. You'll notice as we go through this, all these paths end with confirm that the design rates using PC bars, which is the load rating program that ODOT was using at the time. And the point here is that they've had some problems with that in the past, and they want to continually remind designers that whatever they do, they have to come up with a working load rating when they're done with their design. So if you don't meet the S/100 requirement, the policy then kicks you over to stiffen your design. What they mean by stiffen is increase plate sizes, web depth, whatever you can do under the constraints you're operating under, up to 25% of the weight of the girder in an effort to reduce those deflections. If you're successful, you use the stiffened girder and proceed with line girder analysis. Design the bridge that way. If you are not successful, you're then forced to perform a refined analysis. And what they mean by refined analysis is any form of analysis that acknowledges the cross frames. So at a minimum, a grid analysis, but that's at the designer's discretion. And once you go to grid analysis, the criteria changes to twist, which can be taken directly from the analysis results. So you check for less than 1/8 inch per foot. You then kick back into the stiffen and the design option if you can get that to work. It doesn't mean stiffen it twice. It assumes you've gone back to the original optimized design for the grid analysis. So you can then stiffen above 25% relative to the optimal design and attempt to meet that 1/8 inch per foot. If you still cannot meet it, they recommend then you go to an internal lean-on system Then if you still cannot meet it, they recommend going to an external lean-on system. Now by the time you've reached this point, it's probably time to reevaluate your design beyond just an external lean-on system, because the application of external lean-on is kind of site-specific and may not necessarily make any sense for a given bridge. But the point being, once you reach this stage, you need to start looking at alternatives to conventional erection, because you're going to have a large twist problem. So now going back and starting on the structures with a greater than 45 degree skew, it's essentially the same policy. You just skip all the line girder analysis. You go straight to the refined analysis and measure twist directly, and then follow the same path. So that's the analysis policy. Related to end cross-frame conditions, for skews greater than 30 degrees, ODOT recommends that you not put in the end cross-frame diagonals at the time of the deck placement. And its designers should note that this creates a temporary stability problem during the deck pour, which you usually need to deal with external braces of some sort, but it does does eliminate a lot of potential problems with those end cross frames. Beyond the twist, they also produce a lot of lateral force, which can shear off anchor bolts, that sort of thing, at the end of the bridge. Okay, and then I'm going to talk briefly about how Midas Civil can be used as a tool in the analysis of skewed bridges. One of the very useful features is stage construction analysis. So if you want to consider a multiple stage deck pour, you can apply load in different stages and let's see, this slide, okay, there we go. You can apply load stage by stage and look at deflections during each stage. The most accurate model is, as we talked about, is to use shell elements for the webs, and then you can either use shell or beam elements for the flanges. Both produce good results, and you can get a very good representation of the behavior of the girders. So a multiple stage analysis of a skewed bridge might look like this. Have a stage for the self-weight of the girders. You can apply scaffolding loads using a couple between the flanges, which will also produce twist in those exterior beams. And then each stage of the deck pour can be added using a different construction stage. So here you see the deflection due to stage 1 deck pour. And you can see the deformed shape that we talked about earlier, with each end of the bridge twisting in opposing directions. And one of the advantages here of using beam elements for the flanges is that you can directly extract the lateral bending stresses from those flanges. From the beam elements used to model those front flanges. And this is something that can't be calculated in a 2D model with straight beam elements, since the warping stiffness of the girders isn't included in those models. Here you can see the stage 2 deck pour, slightly different deflected shape. And the stage 3 pour. So the message here is that with a detailed analysis, twisting can be accurately calculated, and Midas Civil provides you all the tools you need to do that. And hopefully this presentation has provided you with some ideas of how to deal with the problem once you know what the twist is. So that concludes my presentation. I think we can take questions now. Okay, I just figured out how to view the questions people are sending me. One question is, can you comment on deck rebar for skewed bridges? Generally, I believe that the number, the cutoff is something like 10 degrees. ODOT recommends turning that 90 degrees to the girders, just because your spans start to get very long if you skew the rebar on a heavy skew. You also don't want to get the two mats of rebar that close to parallel to each other. Question is, how do you actually measure the twist using computer FE analysis such as Midas? You can't get, there are many methods in Midas. You can get measured node rotations in Midas. You can also, if you have a multiple node element like a plate element girder, you can look at deflections between nodes in that element to measure the deflections. Like if you're looking at the slope of the web, you can take the top and bottom node of the web and get a differential slope between those two. What type of connection between the cross frames and the girders is used in the FE model? We're using a rigid link between the cross frame elements and the girders. If you go to a really detailed plate element model, you could directly connect those, or you could put in the intermediate stiffeners and connect those directly to the cross frames. We've never gone that detailed, generally for design purposes. Generally, it's a rigid link between generally the flange node directly to the truss element. In the 2D grid model with truss bracing, how did the offset of the brace form the center line of beam is modeled? Oh, that's that again. So it's talking about the 2D grid model with the truss bracing. We used rigid links between the girder elements and the truss members to model that link. So we just assume that the stiffeners there provide a rigid connection. Question, is the presentation available for download? I believe Midas is going to put that up. If they don't and you want to have it, email me and I can get it to you. There's a question about integral indents on skewed bridges, and yes, that an integral indent is basically an in-cross frame, except it's much more stiff. So the same policy applies, that for a heavily skewed bridge, you would leave that unpoured until after the deck pour, because that will restrain those girders at the end and force them to twist just beyond the indent if it's in place, and it'll put very high stresses in the flanges. Question about shell elements. For the purpose of what we're doing, a shell element and a thick plate element would be the same thing. It's just an element that can take bending along with in-plane forces. And it's probably the most appropriate thing to model a web action in a girder. There's a question about AASHTO recommending a 10 KSI allowance for flange lateral bending. I think that's if you have staggered cross frames. I'm not sure exactly what provision of the code you're talking about, but I think as long as your cross frames are in line across the width of the bridge, you don't need to consider that. I'm not sure if that's in the current AASHTO code, but I know that was there at some point, that you put an allowance when you have staggered cross frames. You need to make an allowance for flange bending if you're not doing a detailed analysis. Then there's a question about staggering the diaphragms. rather than having diaphragms in each bay. And yeah, I know there is a school of thought that there are advantages to that. It does put more bending in the flanges because you're forcing, that torsion into the flanges. It does soften up your cross-frame connections. If you were going to do that, I would recommend that you do a model including elements for the flanges, a 3D model of some sort, and look at that lateral bending stress. Question is the method of detailing the diaphragm fit placed on the plans in Ohio. It's in their material specs for steel girders. By default, it is steel dead load fit. If it's going to be anything other, there needs to be a plan note stating that. That's all the questions I'm seeing so far. If you do want me to send you the presentation, my email again is travis.butts. Here it is right here. travis.butts@bridge.wmv.com. Feel free to contact me with any questions, or I can send you the presentation.
All right, Travis, thank you again for answering the questions. So please send us, if you have any more questions, to Travis, or send it to our email at microsoft@user.com. We will be sharing the recording in a couple of hours, and if you want the presentation files, you can also contact Travis. And thank you so much, everybody, and you have a great day. I will be ending this session and waiting for your emails. Thank you. Bye.